For years, the recipe for a better language model felt simple. Make it bigger, add more parameters, and the loss goes down. Then in 2022, DeepMind published a study called Chinchilla that quietly rewrote that recipe. It found that most of the huge models everyone was celebrating were actually badly undertrained. Today we're breaking down what Chinchilla scaling means, why it embarrassed the giants of its era, and why it's the reason modern models are trained on trillions of tokens. Now, to feel why this landed so hard, you have to see the assumption it overturned. Earlier scaling work from Kaplan and colleagues pointed builders in one direction. Given more compute, spend most of it on more parameters. Grow the model, keep the data roughly where it is, and you win. So the whole field raced to build the largest network it could afford. Then Chinchilla repeated those experiments far more carefully and reached a different answer. For compute-optimal training, model size and the number of training tokens should grow together in roughly equal proportion. A rough rule of about 20 training tokens for every parameter. Data was being starved of feed size. Here's the finding laid out as a simple recipe you can actually follow. Start by fixing your compute budget. That's the real constraint. In practice, you don't get infinite money or infinite chips. So the honest question is how to spend a set amount of compute as well as possible. Then balance size and data together. Instead of pouring almost everything into more parameters, you scale the model and the training tokens in step, aiming at roughly 20 tokens for every parameter you add. That points you toward a smaller model trained on much more data. It sounds backwards, but a leaner network that reads far more text ends up using the same compute in a smarter way. The parameters you save get spent on tokens instead, and the model actually learns from all of them. And the payoff is that this balanced model beats the bloated one. Same compute, better result, because you stop starving a giant network of the data it needed to actually learn. The oversized model wasn't smarter, it was just hungry, and nobody had noticed. So let's pin down the 3 ideas that make Chinchilla matter. Most big models were undertrained. The headline-grabbing giants of the day had far more parameters than the data they saw could justify, leaving real capability on the table. They looked impressive on paper, but they were never fed enough to reach their potential. Scale parameters and tokens together. Compute-optimal training keeps them roughly in balance. And the DeepMind proof was Chinchilla itself. 70 billion parameters trained on far more data, beating the much larger 280 billion parameter Gopher on the same compute. Smaller on more data wins, and it's cheaper to serve. A leaner model doesn't just match the big one. It costs less every time you run it at inference, which is why the lesson stuck. All right, 4 takeaways to carry with you. Chinchilla, from DeepMind in 2022, showed most large models of the era were badly undertrained for the compute they used. For a fixed compute budget, scale model size and training tokens roughly together, about 20 tokens per parameter. Chinchilla's 70 billion parameters beat the 280 billion parameter Gopher on the same compute, just by training on more data. This is why today's models are trained on trillions of tokens. If you enjoy having AI research decoded like this, Standarity.com has more explainers waiting for you. Come take a look.